Now we have to find the equivalent resistance of the network of 12 resistors connected in a cube across the edge. The cube is AB, CD, EF, GH. And suppose we consider the edge AB, so current is coming at A and coming out of the terminal. This is AB is the edge across which we have to find the equivalent resistance. So by symmetry we can say that point D and G are symmetrically equivalent. So current is suppose I1. And now we can say that D is at potential say V1. So H is also at the potential V1. And by symmetry, current incoming to B is I1 from C and I1 from E. Therefore, this C will be at potential V2 if then E is also at potential V2. So we can make a equivalent circuit that this is terminal A, this is terminal B. Across them there is a branch. This branch is AB, which has a resistance R. Then from A to D and H, there are the two resistances which is at the equipotential point V1. So these two resistors are in parallel. Similarly, another point is of potential V2 across which two resistors are in parallel. Between V1 and V2, if we see there is a branch, this is HG, and there is another branch DE, DC. So these two are in parallel, therefore these two resistors are in parallel. So the remaining points are G and F. Suppose we consider that this G has the potential say V3 and F is having the potential V4. So these V3 and V4 are 2 points. Then from the point of potential V1, there are the two resistances. One is HG, another is GD. So these two resistances are in parallel. Similarly, from point of potential V4, there are the two resistors which are having the same potential V2. So these two resistors are in parallel. So there are two resistors in parallel. And between GF, there is resistance R. So this is the effectively the net equivalent circuit of the given cube. Now we can find the equivalent resistance by simply solving. This is parallel combination, so value will be have R by 2. Another one from V1 to V3, it is also having two resistors in parallel, so their equivalent value will be R by 2. And this R by 2, R and R by 2 are in parallel. So effectively we can now reduce the figure as these are 2 points V1 and V2 having the two parallel resistors. Then there are two parallel resistors to point A to B there is a resistor R, and from A to V2 there are two parallel resistors, and in between there is a resistor which has the value R by 2R. This is 2R. This implies that now we can simplify that these two resistors are in series parallel, so its value will be R by 2. These two resistors are in parallel, so it is R by 2. And these three resistors are now in parallel, so we have to find this value. So this is A, this is B having the resistance R. There is a resistance which is R by 2. There is a resistance which is R by 2. This point is at potential V1. This point is at potential V2. Now we have to find the equivalent resistance of these three resistances which are in parallel. So 1 by R dash is equal to 1 by 2R plus, and these two are in parallel which have the value R, so it is 1 by R plus 1 by R. So it is 2R, and in numerator we will get this is 5. So R dash will be equal to 2R by 5. So this resistance is 2R by 5. Here this 2R by 5, R by 2 and this R by 2, these three resistors are in series. So we can write that this circuit is reduced in the form, this is AB, there is a resistor R, and there is another resistor which is the series combination of r by 2, 2r by 5 plus r by 2. So it is simply r plus 2r by 5, or it is equal to 7r by 5. This 7r by 5 is in parallel with r. So we can write that terminal AB has a resistor R equivalent which has the value, and this R equivalent can be calculated as 1 by one of the resistor. That means we have to write 1 by R plus 1 by another resistor is 7R by 5. So we have to simplify it. 1 by R plus 5 by 7R. So it is equal to 1 by, taking LCM, this is 7R. Here it is 7 plus 5. That is equal to 1 by 12 by 7R, or it is equal to 7R by 12. This is the answer.